Yeah? Okay. So hello, my name is Ariel Kellison, and I am presenting on my paper, A Machine-Check Direct Proof of the Steiner-Lehmus Theorem. I'm a PhD student at Cornell University. So first off, what is this paper about? Well, it provides a direct proof of the Steiner-Lehmus Theorem, and a direct proof in particular is one that is completely independent of the law of excluded middle. The paper goes on, it guarantees an independence from the law of excluded middle using a proof assistant, and in particular the Newpearl proof assistant, which was developed at Cornell University, that implements a constructive logic. And we also introduce a novel set of constructive axioms for Euclidean plane geometry in order to derive the proof. So the Steiner-Lehmus theorem is an elementary theorem from Euclidean geometry, and it is stated as this: if two internal angle bisectors of a triangle are equal, then the triangle is isosceles. It's quite old. It was first proposed by Lehmus in 1840, and the first proof was published by Steiner in 1844. So let us take a look at this elementary diagram. So again, if the segments DC and EB in this triangle are congruent, and indeed they bisect the angles that they correspond to, that is, gamma is equal to delta and alpha is equal to beta, then the sides of our triangle are congruent. So AB is congruent to AC, and the triangle is therefore isosceles. So Steiner's original proof from 1844 immediately assumes the law of excluded middle. So if one wanted to assume that the angles alpha and delta can be unequal, say in particular that alpha is strictly greater than delta, the impossibility is easily shown as follows. Steiner then goes on to use a handful of theorems from the elements. And it's important to note that all of these theorems are from book 1 of Euclid's 13 books of the elements. So the proof is rather close to Euclid's original axioms, which date back to 300 BC. This means that we shouldn't have to do too much digging in order to determine all applications of the law of excluded middle that are used in the proof, one would hope. So the controversy over direct proof goes back to 1852, when Sylvester, a geometer of the time, makes the comment that any geometrical demonstration of the theorem is necessarily indirect, and in particular that no other form of the proof than that of reductio ad absurdum is possible. Despite Sylvester's comments in 1852, in 1937, a survey is published by Henderson with no less than 7 supposedly direct proofs. And it's important to note that all of these proofs use theorems from books 2 and 3 of the elements. So unlike Steiner's first proof, which only used theorems from book 1, we are now going forward to books 2 and 3. So one would assume that we have many more theorems, auxiliary lemmas that are used in the proof to try and find any applications of law of the excluded middle in. More controversy. In 1943, we have some comments from someone named McBride, who says that if Euclid Book 1, Proposition 14, 29, and 32, and furthermore the Pythagorean theorem have no direct proof, then the bisector theorem, which is the Steiner-Lehmus theorem, has not been proved directly, nor is it ever likely to be. Okay, but again, in 1970, and you'll see I have red checks for those who believe there is no direct proof, and then I have green checks for those who say they are in favor of a direct proof. So in 1970, we have a publication again of a supposedly direct proof of the Steiner-Lehmus theorem. But then in 1974, we have some commentary by Lewin. Any direct proof is rightly discredited if it depends on indirectly proven lemmas. Coming up a little more recently, Conway in 2014 says, no, there cannot be a direct proof, Conway and Riba. But then again, they do leave a little bit of room. Possibly there can be. Most recently, in 2018, Victor Pambushian provided a proof of the existence of a direct proof of the Steiner-Lehmus theorem using classical logic. This is a nice result, but it does not actually provide the direct proof itself. So the paper claims to have a direct proof of the Steiner-Lehmus theorem, and the question is now, how do we guarantee that this proof is direct? First, we start by introducing a constructive set of axioms for Euclidean plane geometry. Then we go on to formalize the necessary theorems from book 1 of the elements. And then we derive our Steiner-Lehmus theorem using only those theorems from book 1 of the elements and completely inside of a constructive setting. Okay? But the guarantee is that we have done all of this inside of the Newpearl proof assistant, which implements a constructive logic and from which we cannot use any hidden assumptions of law of excluded middle. The nice thing about working in NuPro is that there's an implementation of the constructive reals, and so we can prove the soundness of our axioms with respect to these constructive reals, removing maybe any more questions of whether or not we've used inappropriately the law of excluded middle in our proof. Okay, so in the guarantee of a direct proof, I'm first going to discuss a little bit the constructive axioms that were used. So going back to previous constructive axiomatizations of geometry, there are several. And for the most part, they use an atomic binary apartness relation on points. And from the constructive perspective, this is very useful. We can, if we have some evidence that 2 points are completely separated from one another, we can do something like a construction of a segment between these 2 points. And in general, we define equivalence negatively in terms of this apartness relation, which I think is fairly intuitive, so that if 2 points are equivalent, we cannot witness any separation between them. It's also common to use an atomic ternary leftness relation on points. So if we see that the point C is strictly separated in this case and lies to the left of the points A and B, and this gives us some notion of orientation on the Euclidean plane. And it's also common in previous axiomatizations to take congruence and betweenness as atomic relations. What's different in this paper is that instead of using an atomic binary apartness relation on points, we use an atomic quaternary apartness relation on points, and this gives us the idea, the notion that, for example, the segment CD is strictly greater than the segment AB, and this relation again is on points. The paper also takes a ternary leftness relation on points and defines apartness in terms of the quaternary relation and then equivalence in terms of this binary apartness relation. Importantly, rather than taking congruence and betweenness as atomic relations, these are now defined in terms of apartness and leftness. So there are 5 construction postulates. So the axioms are separated into 2 groups. The first group consists of these 5 construction postulates, 3 of which are typical straight-edge and compass constructions from Euclidean geometry. So firstly, plane separation, or the application of the straight edge twice, gives us this point X, which witnesses the intersection of 2 lines. And then we have, for example, straight edge and compass, which gives us the point of intersection, or at least one point of intersection, between a circle and a line. And then we have the application of the compass twice, from which we actually only need the existence of one of the points of intersection between the 2 circles. Okay, so there are 5 construction postulates. The second set of axioms are universally quantified. So for example, axiom U6, which is highlighted here in red, says that if the point B lies between points A and C, and these points are strictly separated from one another, then we can say that the segment AC is strictly greater than the segment AB. Awesome. Okay, so that's a very brief introduction to the constructive axioms that were used in the proof of the Steiner-Lehmus theorem. I'm not going to go into detail on the theorems from the book 1 of the elements that enabled us to derive a direct proof, but I will say that there were 28 of the 48 propositions necessary from the book 1 of the elements in the proof. There are about 1,500 proof objects required for the proof of the Steiner-Lehmus theorem in NuPro. And we also had to provide constructive definitions for angle sum, angle ordering, and parallel segments. Okay, but going back to the original controversy over whether or not a constructive proof exists, so one that does not use the law of excluded middle, one might wonder, how did we get away without using law of excluded middle in the proof of any of these intermediate 28 propositions? So in constructive logic, there's a useful distinction between stable and decidable propositions. In particular, stable propositions are those propositions which are applied by their double negation, while decidable propositions are those propositions for which there is an algorithm that allows us to compute either P or not P. And decidability is a strictly stronger notion than stability. And while not all propositions in constructive logic are decidable, the double negation of the decidability of arbitrary propositions is constructively valid. so that in the proof of any proposition P, we can assume the double negation of Q or not Q for any Q. Why is this important? Well, in the proof of stable propositions P, one can eliminate the double negation from arbitrary proposition Q or not Q to arrive at the decidable proposition itself. And importantly, negated propositions are stable propositions. Why is this important for the proof of the Steiner-Lehmus theorem? Well, before I said that congruence and betweenness were not taken as atomic relations in the theory of geometry that's presented here. Indeed, congruence is defined negatively. So going back just a step, all negated propositions are stable propositions. And so we can eliminate double negation and use case distinctions inside of our proof of the Steiner-Lehmus theorem. So here is a portion of the new Pearl proof. Okay, so just quickly, at the very top here is a statement of the Steiner-Lehmus theorem in new Pearl, and I've just highlighted the difference in notation here for betweenness between what I introduced earlier and what actually we see in the new Pearl presentation of the proof. Okay, so just to point out a few things. First off, in the proof of the Steiner-Lehmus theorem, we start off by introducing or constructing a parallelogram inside of our triangle. And later on, in order to distinguish, to finish the construction, we have to use separation of points Q and B. So we must have some witness of separation on the points Q and B. Now, again, because the conclusion of our theorem is stable, we can reason by cases. So in the blue rectangles here, I've denoted that suddenly we have two branches in the proof, where in one case, we can reason on Q being strictly apart from B, and in the other case, we have an equivalence between Q and B. And again, we can make case distinctions here, where later on in the proof, we would like to know whether or not the side lengths AX and CY are congruent. And this is very much toward the end of the proof. And we can say in the highlighted boxes here, you see that in one instance, again, in one branch of the proof, we have that AX is strictly less than CY, while in the other branch, we have that either CY is strictly less than AX or they are equal. And so this shows a few applications of using the stability of our conclusion to reason by cases. And although we're not using the law of excluded middle, we have some different constructive reasoning that allows us to use case distinctions within the proof. Okay, so that is my contribution to the long history of this problem and also the end of my talk. Thank you.
Thank you very much for the fascinating work. So we have, now we're taking some questions. Is there any local question?
Yes, hold on. How close does your proof follow one of the previously published ones, or did you work this out all yourself?
Yeah, so thank you. Yeah. If I look back here, there is a 1980 proof by R.W. Hogg that actually doesn't make any claims to whether or not it is a direct proof. The construction is very similar to Hogg's, although just as Steiner's theorem does, he immediately applies law of excluded middle early on in the proof. But if you look at, for example, Steiner's proof in addition to Hogg's, the reasoning is very similar in all instances. So this constructive proof is not, it's not that it's necessarily so different from all of the many attempts that came before it, so much as its derivation is completely absent from the law of excluded middle. Yeah.
All right, so this answers one of the online questions by Dominic, if the original proof somehow recognizable in your proof. So let's post the question from Dan Frumin, please.
Yeah, I mean, just to return to that, it's an extremely old theorem with only requiring so many lemmas from the elements. So I would assume that many of the theorems would follow similar patterns, yeah, or many of the proofs.
All right. So the question is, what does the apartness relation CD greater than AB mean?
The apartness relation, CD. So I have this atomic relation. CD is strictly greater than AB is a quaternary apartness relation on points. And intuitively, we use this to say that the segment represented by a point, 2 point CD would be strictly greater than AB. I'm sorry, I feel like that's really intuitive. I'm a little confused. Is there something more to that question?
I'm not sure. So Dan will.
It's a completely.
Okay. I think he just wanted a clarification about what was the meaning of this relation that you introduced.
Yeah.
All right. So a question from Benjamin Werner, please. Can we post it? Is it imaginable to plug an interface like Euclidean to neutral?
I'm sorry, can you repeat the question? Or maybe I can see it.
Is it imaginable to plug an interface like Euclidean to neutral? I'm not sure if Euclidean refers to a tool or you mean Euclidean, Benjamin. Feel free to raise your hand and ask the question live if you want.
Can I stop there?
Ariel, does the question make sense?
Luke, oh, I'm sorry. I'm not familiar with the interface Euclidean, I suppose. Is it like a graphical interface for proving geometric theorems? I assume.
Benjamin.
Yeah, exactly. It's you as you see, I'm a little obsessed by graphical interfaces, but it's quite a fabulous website actually, euclidean.xyz.
Okay.
And where you have a lot of quizzes in Euclidean geometry, and obviously there is a logical. I'm not involved in that at all, but obviously there's a logical tool behind it, deciding whether you have constructed the right point or not.
Yeah, I think that's interesting. So early on in the New Perl development of geometry, we actually embedded GeoGebra in New Perl so that you could go through the proofs in GeoGebra while you were doing the constructions in New Perl. We didn't end up getting very far with that or continuing on with it, but it's certainly something that could be done.
All right. So we have a question. Sorry, let's see if we have any other local question, please.
We do. Hold on.
Yes, please.
Hi, I'm Joe. I am curious exactly where the paper you presented or the discussion here relates to the sort of long history of this problem. The previous attempts to have the so-called sort of direct proofs, they were working from Euclid's axioms of geometry, right?
Yes.
Sort of all of the original ones. And then here we have a constructive derivation of the theorem from your I guess one axiom, the 4 parts inequality relation?
So that's the 4 parts is the atomic relation. So we use the atomic relation in our axioms.
Right. So the axioms that you're working from are different from Euclid's axioms, correct?
They would necessarily have to be, for formalization inside of a proof assistant.
Gotcha.
Yep.
Okay. So does this? I guess this isn't necessarily a constructive or a direct constructive proof of the theorem from Euclid's axioms, but it's like from a slightly tweaked version of Euclid's axioms.
I mean, so going back to the methodology here, we have to start off with a constructive axiomatization for Euclidean plane geometry. So I guess my claim is that Euclid's original axioms are not constructive in the sense of constructive mathematics. Yeah.
All right. Now we have a concrete question, online question from Antal. If we can post it. If we have 3 collinear points ABC, is AC greater than AB or not?
So let me just refer to my definition of collinearity. Sorry, if we have 3 collinear points, ABC, can you repeat?
Yes, if we have 3 collinear points, ABC, is AC greater than AB or not?
And I assume that you mean like the definition of strictly greater than that I have here.
Strictly greater than, yes, strictly greater than.
Yeah. So just by collinearity, you have 3 points. You don't know the relationship between those 3 points to one another.
Yes, I guess. I guess the question assumed that they are in that particular order, A, B, and C. which probably means
if I know that those 3 points are collinear using the definition that I have here, no, I cannot derive that any strictly greater than relation between those 3 points. No.
Is not strictly greater than. Okay. All right. I hope this answered the concrete question. Now, any other local questions?
It appears not.
So let me ask a question. Let me use my privilege, session chair, to ask a question too. Can I infer from your proof that let's say if you use your axioms for geometry, which are close to Euclid's axioms, if I understand, and you use intuitionistic first-order logic only, so you don't use this higher-order logic of neutral, but really the first-order theory in intuitionistic first-order logic, do you get a proof of the theorem? Or can you even I guess you can formulate the theorem. Do you get a proof of it?
If you're using, so I haven't used any of the higher order logic of neutral to derive the proof. Is that the question? Can it be done? Is it completely first order, like in the same sense of like Tarski's theory being a completely first order theory of geometry?
Okay, so this would work if you would not have any higher order features, because that's a derivation in a higher order logic. So you are saying that it would work in first order intuitionistic logic, your derivation.
The derivation should work in first order intuitionistic logic.
I see. Okay, so the answer is yes. Okay.
But I haven't done that, so I make no claims.
All right. Thank you. So if there are no other questions, let's thank Ariel again.
Thank you.
So Ariel, actually, if we can pose this question from Oliver to you, why do you think it is important for a mathematician or for a logician? Well, I guess let's stick to mathematicians. Why is constructive reasoning important?
Okay, that's a pretty general question. So why is a constructive proof important? I think, okay, why is a constructive proof of the Steiner-Lehmus theorem necessarily important, or just in general constructive proof?
Yeah, I mean, feel free to give any nuance you wish to this question.
Oh dear, put on the spot. Okay, I mean, maybe from just a philosophical standpoint, we might care to not use the law of excluded middle. I mean, constructive proofs lead us to like computational results, I guess, that if we were to use the law of excluded middle instead, we wouldn't necessarily get. Maybe I'm not doing constructivist justice with that explanation, I suppose.
All right, thank you. Just a clarification from Oliver. He says, to be clear, I certainly think this paper and talk is great work. So, all right, thank you very much again.